pretty clear from this whole Congress that there is still interest in sending a manned crew to Mars. I will not explain you where Mars is, but I will explain you some challenges. The most important challenges for this research was radiation, which we need to shield the crew from. And we have different radiation methods, but the most effective one is to use a high mass of materials. And different materials have different shielding properties. Here you see Martian regolith, and here you see water. So although water performs better than regolith, you still need a high mass. And this high mass is a problem when you think about the EDL, because we cannot land high mass yet on Mars. It's highly difficult and it costs a lot. So this stresses the importance of the use of in situ resources. Also another challenge is the extreme temperature fluctuations between day and night. So my design location is the Jezero crater, and there throughout the day you have temperatures of minus 20 degrees Celsius, and at night you have minus 80 degrees Celsius. So this led to my problem statement that if we are sending a crew, we really need to protect them from this really harsh Martian environment. And my research question for this thesis was, which in situ materials and forming techniques are suitable to create an outer shell for a sustainable habitat on Mars, which protects the crew from this harsh Martian environment. So looking at in situ materials, we mostly have two. The first one is regolith, which is widely available throughout the whole planet. And the second one is ice, and ice is found underneath the regolith. And it was a really interesting material for an architect and an engineer, because first of all, it's an excellent radiation shielding material, and second, it's translucent. So it will be able to let daylight shine throughout the structure, which affects the psychological experience of being isolated. So another aspect is that ice will most probably be mined for the Mars Ascent vehicle. So because we are already bringing all the tools necessary to mine the ice and process the ice, I will reuse these tools to build my habitat. I researched also how to build with ice first on Earth, and the most well-known example is of course the igloo, but we have some ice palaces and hotels, but those are really small span structures, and most of all temporary, because we have different temperature fluctuations here. So if we want to create bigger structures, we need some reinforcement. And on Earth we use pykrete, which is a mixture between snow, ice and wood pulp. And TU Eindhoven actually did some great research about really big domes of 30 meters big. However, that's not very viable if we want to build on Mars. So I performed some experiments using in situ reinforcements. And here on the top you can see just a plain ice structure, and you see we have big cracks throughout the whole specimen. So I tried to add some HDP and PP, so recycled mission design plastic. But as you can see, it doesn't mix as well, and we also have those big cracks. The same goes with the sand, which is kind of a mimic analog for Martian regolith. It doesn't mix well, and also it does not improve the building qualities at all. One thing I saw my table salt there, and we know that salt is present on the ice in Mars. So it's NaCl, natrium chloride salt, and I've added that to my specimens as well. And what we see is that most of all, the reinforcement mixes better, but the whole structure of the ice changes. So it's a really granular ice, and instead of having those big cracks, it actually only, when it breaks only a little part of it. So I made some more decent experiments, and I used the standard concrete, the STM-C39 testing methods. And I tested my ice in ambient temperature, so at plus 25 degrees, but also at minus 70 degrees to mimic the night on Mars. And so you can see here that I put it under compression and measured the strength. And in the middle you see a specimen after testing with no salt at all. And you can see that it's really broken in little different pieces. And here we see an ice specimen which is reinforced with salt. This one has 10 parts per thousand, which is about 1% of natrium chloride. And we see this really clean cut, which, yes, as an architect we really like. And also the performance is increased. So with no salt, we have a 1 MPa force that it can sustain. And the reinforced with salt is increased to 4 MPa, so it's a large increase in compressive strength. However, we need to build with this ice, and I made some small research, and because it has to be built remotely, I used additive manufacturing as a solution. And so to test that, I built a linear additive manufacturing frame and tried to build a structure at minus 30 degrees. The results were a highly irregular shape, and an interesting thing is that some cracks appeared while building the shape. However, when you build a new layer, the water will flow through the crack and it will freeze, and upon freezing it expands, so it actually creates a really strong structure. And so I applied a force on both sides of the structure, and what you can see is it broke in one straight line, although it is a very irregular shape. So that was very interesting, and also the resistance was very great. So it shows that building layer by layer most already reinforces the whole structure, and that is also stated by theory, where they say that river ice, because of the flow of the river, it builds layer by layer as well and creates an overall stronger ice. So with all these aspects taken into account, I designed a habitat which is called the ice hab. And here you can see 3 steps of the ice hab. So on the bottom, first we have 2 modules which will land and then will be deployed with the floors, the walls, the interior, as well as the EVA hatches. Then second step is an inflatable plastic membrane which is filled with local ice or water which will freeze up. And then lastly we have a additive manufacturing wall ice. The reason why I have 2 walls is mainly redundancy. Because if we look at the first wall, which is optimized to be in full compression, we see that it's additive manufactured. However, the TRL, the technology readiness level of this technique is very low. It hasn't been tested yet. So this will serve as kind of an experiment to see how it will react in the Martian environment. And then for redundancy, we have a second wall, which is within an inflatable PTFE, translucent plastic membrane, as kind of a safe, which has a higher TRL because it can be tested here on Earth. And then finally, I also have an insulation layer of aerogel, which is also translucent. So this whole system will create an intermediate climate where experiments can be made, and then inside we have a nice radiation shielded indoor climate. And as you can see, I have 2 models, and that's because mainly I want to combine engineering requirements with architectural requirements. So 2 modules is mainly for redundancy, but it's also because I want to separate the living from the working quarters. I want to create an interesting routing, and that's all to kind of counteract the boredom of being isolated. And so my conclusions are that I try to build